Hi class, this is hopefully a short video, maybe longer than some of the videos we've been listening to, 10 to 15 minutes, but certainly no longer than 15 minutes, and I'll try to keep it short. The main topic that we're going to talk about in 2 slides is going to be the renal countercurrent multiplier system. There are five things that come out of this that are important. So let's talk about those first. And the crux of this is you're trying to create a hyper osmotic interstitium and a hyper osmotic bottom of the loop here. And we'll talk about why that's important. So there are 5 keys to medullary interstitial fluid hyperosmotic state. Number 1, you need the countercurrent anatomy of the loop of Henle. All right, this is the loop of Henle, countercurrent. 2, you need reabsorption of sodium chloride in the ascending loop. This is the ascending loop. Number 3, you have to have impermeability in the ascending loop to water, and we do. Number 4, we have to be able to trap urea. So urea goes around, gets trapped, and goes round and round. Number 5, you need hairpin loops of the vasa recta. You need a hairpin loop of the vasa recta. So those are the 5 important keys. Now, what is this countercurrent multiplier system? This is a nephron. The glomerulus and Bowman's capsule has been cut off. When we bulk filter all of the substances out of the blood from the glomeruli into the proximal tubule, we equally absorb water and solutes. And so the osmolarity at the proximal tubule, the beginning of the descending limb, is about 300, which is roughly the osmolarity of arterial blood. What starts to happen? What starts to happen is as you move down the descending loop of Henle, you have only water reabsorbed because you have aquaporins in this area here in the membranes, and water moves down its electrochemical gradient. As you reabsorb more and more water, the concentration of solutes, therefore the osmolarity of the substance, the fluids in the descending limb increases until it peaks at about 1400 mils, 1400 milliosmoles per liter, which is almost 5 times what the rest of the body sees. When we make this turn to the thin ascending loop and then the thick ascending loop, water is no longer reabsorbed. Only sodium chloride and some other solutes are reabsorbed. And because of this, the concentration, the osmolarity in the thin and thick ascending loop begin to decrease until they decrease to 80, right? 80, which is essentially 1/4 of the osmolarity of the blood. As we go back down through the distal tubule and then the collecting ducts, we will eventually create a hyperosmotic urine, which is what you want, which is what you need to be able to survive in times of drought, right? We evolved in the oceans where there was plenty of water, and we made the transition to land, and the kidney is one of the major organ systems that allowed us to do that. Okay, so what is a countercurrent multiplier? You have 2 sets of currents going here. So you imagine that all 3 pieces here, the descending limb, the thin and thick ascending limb, the distal and collecting ducts are all very, very close to one another. You have 2 currents. You have a current that comes up, down, a current that comes up, So that's the difference between these two. And then you have a current that goes up versus another current that goes down. So each one of these, the down versus the up, is considered a countercurrent. So this is one countercurrent. This is another countercurrent. So countercurrent. What ultimately happens is because of this loop, this countercurrent, the interstitium, the area between these parts of the loop of Henle, right, become hyperosmotic. So because of this hyperosmoticity that is created mainly by the ascending limb, you again get water reabsorption because water follows its concentration gradient downhill. Okay, so without this shape of the loop of Henle, without these hairpin turns, you don't get a countercurrent multiplier. Now the multiplication part is that because of the countercurrent, because you have increasing and then decreasing osmolarities, you're essentially multiplying, right? You're multiplying, you're doubling the osmolarity from here to here. You're increasing it again from here to here. You're increasing it again from here to here. You're increasing it again from here to here. And then you're decreasing by large amounts, So the countercurrent multiplier makes it so that you have a hyperosmotic interstitium. If you don't have a hyperosmotic interstitium, if all of these numbers are 300 all the way along, you can't reabsorb water. So that means you're going to produce a highly hypoosmotic urine, and holding on to water is going to be extremely difficult. So instead of needing to replace roughly a half a liter to a liter and a half of water a day, depending on how active you are and what type of environment you're in, you would have to drink significantly more water. And that would be very difficult, and we would never have been able to have survived in the desert regions, in very, very hot regions and jungles. So that's the countercurrent multiplier. Now, once this gradient is established, right, you have this highly hyperosmotic interstitium in between these tubules, which allow for the reabsorption of water, right? That's what this system is doing, which then produces a hyperosmotic urine, which is what you want to do because you want to conserve water. Here's to give you an extreme example. There is a type of mouse that lives in a desert, rodent, whose urine is so concentrated. So their countercurrent multiplier system is so efficient that their urine is actually solid. So that's an extremely efficient modification and adaptation over evolutionary time that takes this system and supercharges it. Okay, once you've established this hyperosmotic interstitium, you want to keep it. So you have these capillaries called the vasa recta. Now, mind you that we're talking about nephrons here that are juxtamedullary nephrons, right? They're deep, deep within the medulla. These are the ones that are really long, not the cortical nephrons. You have this additional capillary bed called the vasa recta. And the vasa recta has the same shape with the hairpin turn as the loop of Henle. Why? Because imagine the two of these are next to one another, right? Imagine the two of these are next to one another. So let's draw that. Imagine that this thing in green represents the nephron. Which is where they're located. You have this highly hyperosmotic interstitium that allows water to be reabsorbed in the thin descending limb and in other places. If you didn't have a shape of a hairpin turn in the vasa recta, which sits right around the nephron, the osmolarity here in all of this bed would be about 300. And what would happen is this 1400 milliosmoles per liter would eventually wash out because you'd be losing, right? You'd be losing that that you'd be creating a gradient, right? If this was all 300 and this is 1400, right? What would happen? You'd pull water from the vasa recta, and it would essentially wash out this gradient so that it would eventually go to 300, right? Because water would go down its concentration gradient. And then you would no longer be able to reabsorb water efficiently. You then ultimately wouldn't be able to produce a hyperosmotic urine. And if you were far away from water, you would essentially dehydrate and die. So that's the system. These are the locations of each of these anatomical structures, and the reason that this has its shape is because of this shape, and it has to be so. The other thing that I wanted to mention going back to the loop of Henle is that urea, which is a byproduct of protein breakdown, gets trapped. When you get to the cortical collecting ducts here, water and urea are transported across from the collecting ducts to the ascending limb. So about 50%, 55% of urea keeps getting recycled between these two areas. It goes up, comes over, and gets down. Roughly half of the urea is reabsorbed here, give or take 50%, 45% urea here. So you have about 50-55% that's recycled, 50% comes up. Let's say it's 55%, 5% gets reabsorbed, 50% here, give or take, right? These are rough numbers, between 45 and 50%. So the urea recycling also adds to this countercurrent multiplier system, right? So that this is an additional step, an additional piece that, along with this countercurrent multiplier, helps maintain these hyperosmotic interstitial levels. That's it. There's the countercurrent multiplier system. Hopefully that makes sense to you, and have a great day.